Hello viewers, Wagdaruna taking you through the story for A-Level Physics Paper 2. And this video we are still going through the topic of magnetism and alternating current. So in particular today we are looking at calculations on ballistic galvanometer. So these are the subtopics under the topic, and what is ticked means is already available on the platform. What is not yet ticked means will be uploaded with time. So since we are interested in calculations mainly on this platform, complete notes are found in the books I recommend. So physics, there are 4 books: Physics Paper 1, Physics Paper 2, Topical Question Bank and its solutions. Principal Mathematics, there are still 4 books: Math Paper 1, Math Paper 2, Termly past papers with marking guides, and a topical question bank with answers. For subsidiary math, there is only 1 book which contains notes and past papers. For any of the copies, contact the author on this contact. So previously we looked at what we call a moving coil galvanometer. So that moving coil galvanometer was used to measure small currents, okay? But when we modify it a little, it can be used to measure electric charge. And when that happens, it means that it now gets a special name called ballistic galvanometer. So in short, a moving coil galvanometer measures small electric currents, okay? But when modified, it can measure electric charge, and in that case, it is called a ballistic galvanometer. So it consists of a rectangular coil of fine insulated copper wire wound on a heavy insulating former and having a fine suspension. Okay, when the charge passes through the instrument, its coil is deflected and it oscillates with decreasing amplitude about its initial position, 0. So it keeps on oscillating. I think you remember decreasing amplitude means it is like this. So it keeps on reducing until it goes to 0. So here, that's why in this video you'll hear me talk about fast deflection or maximum deflection. Why do you say fast? Because if you don't note this fast deflection, the rest will keep on reducing, so you'll not get the correct measurement out of it. So always when you're using a ballistic galvanometer, we should mention the word fast deflection, because as time goes on, the angle measured or the deflection keeps on reducing to 0. So either use the word fast deflection or use the word maximum deflection. So this charge Q is directly proportional to the maximum, do you see that word? Maximum angular deflection. So either use the word maximum deflection or fast deflection. That means that Q is directly proportional to theta max. When I put an equal sign, I should introduce what we call a constant of proportionality, which is K. So K is a constant of proportionality, and it has a special name called charge sensitivity. I think you remember, okay, in moving coil galvanometer we had voltage sensitivity and current sensitivity, but now we have what we call charge sensitivity. And in this case it will be coulomb per radian. Coulomb per radian or coulomb per division, but you can also get the reciprocal of that charge sensitivity, which will be radians per coulomb. Okay, so before we go to the calculations, we need to see what we call calibrating a ballistic galvanometer. So this involves finding the charge sensitivity of a ballistic galvanometer. So let's first draw a circuit. That is okay. So switch S is connected to X. When switch S is connected to X, the capacitor C charges to a PDV. So when you connect here, it means that this one is out of circuit and the complete circuit is this one. Because there's a voltage supply, the capacitor will keep on being charged until it reaches this value of V. When you change the switch and you connect to Y, the capacitor discharges through ballistic galvanometer. Discharges through a ballistic galvanometer. The first deflection, see the word first, you either use the word first or maximum deflection. So the first deflection, theta max, on the ballistic galvanometer is noted. That means that charge on the capacitor is proportional to the maximum deflection on the ballistic galvanometer. So that means that Q is equal to K theta, but we know that Q is equal to C times V. And a good thing, we know the value of C, capacitance of the capacitor, and we know the PD supply. So I can substitute where there is Q to come up with this expression. So in this case, it means that I know this, I know this, I know this, so I can get K, I can make K the subject. That is what we call calibrating a ballistic galvanometer, for you to be able to know the charge sensitivity. So K is known as the constant of the ballistic galvanometer, and it's measured in coulomb per radian or coulomb per division. So sometimes they can give you the reciprocal. So reciprocal of this constant is radians per second. So when you see the word rad per second, just know that they have got the reciprocal, which is 1 over K. So always be keen with the SI unit put on the constant of the galvanometer. Okay, so there's something we need to know, that is the relationship between magnetic flux linkage and induced charge. We already know what magnetic flux linkage is, and we know that induced EMF is equal to change in flux linkage over time taken. But now how is it related to induced charge? That is what we want to see. So consider a coil of N turns in a circuit of total resistance R, in which the flux linking each turn is changing and has a value of N phi, where this is magnetic flux and this is number of turns in time t. So we have pole pieces provide an external field. Then we shall put a coil. And a ballistic galvanometer. So whenever the magnetic flux phi linked with the circuit changes, an EMF is induced in the circuit. I think we saw that already under the topic of magnetic flux and flux linkage. A current I flows in the circuit due to the induced EMF. The induced EMF E in time t will be given by E is equal to negative N d phi dt. But E is given by IR, if I know the resistance and the current. and I know that current is d/dt, rate of flow of charge. So I can substitute where R is the resistance of the such coil, and the galvanometer, the whole of this resistance, or the whole of this, is what we call R, total resistance. So I'm going to substitute for E to come up with that, and also for I to come up with that. So now here I realize that dt will cancel, so you remain with dq equal to, when this one goes this side, it becomes negative n over r d phi. So if the flux linkage changes from this to this, the total charge that passes through the circuit will be given by integral from 0 to 2, and here integral from phi 1 to phi 2. The n is already here, so you don't need to put it here. So when I integrate, this gives me 2, and this gives me that. Bring in the limits, you come up with that. So take this negative inside to come up with that. When you bring the n also inside, you come up with this. So that means that I can, remember, I know that this is the initial flux linkage and this is the final flux linkage. Therefore, I can write it in words and say induced charge is equal to change in magnetic flux linkage over total resistance of the coil. So that is basically the relationship between induced charge and magnetic flux linkage. There's something we need to note. One, if the coil is moved out of the field to a point where the field is 0, then the magnetic flux changes from phi 1, which is this, to phi 2, which is 0. And in that case, by substituting, will give us this. So now this is the formula. Substitute final minus initial to give you this. So when in somewhere in the calculation, they will tell you that the coil was completely removed out of the field, then you should know that charge is equal to this. When they tell you that the coil is rotated through 90 degrees while still in the field, it means that now we bring in the angle. Remember, flux is AB cos theta. So angle, it means that initially it was 0 degrees, but now it is 90 degrees. When it is 0 degrees, it means it is AB, because cos 0 is 1. When the angle is 90 degrees, it is now 0, because cos 90 is 0. So therefore, the charge now becomes this. It is similar to the previous one, but you look at this third one. When you rotate it through 180 degrees, something is going to change, because phi 1 is here at 0 degrees, which is this, and phi 2 is 180 degrees, which is negative. When it is negative, something is going to change. Do you see what has changed? Here, it was just NAB over R, but now here it is 2 NAB over R. So I want you to remember that when they say it is rotated through 180 degrees, it is now 2 NAB over R. When it is rotated a quarter turn, it is just NAB over R. When it is completely pulled out of the circuit, it is still NAB over R. So always remember that in the calculations we are going to do. So let's start with this. So question 1 says, a long solenoid carries a current which produces a flux density B at its center. Okay, a narrow coil M of 10 turns and area 4 meters squared is placed in the solenoid so that the flux links it normally, and the ends of M are connected. If the charge of this circulates through M when the current in the solenoid is reversed. Do you see this word? Reversed. Given that the resistance of M is this, determine the value of B. So reversed means a complete change of field through 180 degrees. For example, if it was moving in this direction and reverse current, it goes in the other direction. That is a change of 180 degrees. Therefore, the charge will be now 2NAB over R, which is make B the subject to come up with the value they wanted. Then question 2, a circular coil of wire of 24 turns with its ends joined stands with its plane vertical facing magnetic north and south. It is suddenly turned through 180 degrees about the vertical axis. If the radius of the coil is 40 centimeters, its resistance 0.5 ohm, and if the horizontal component of the Earth's field is this, calculate the quantity of electricity set in motion, i.e. the charge. So because it was rotated through 180 degrees, we use 2NAB over R. You come up with, substitute for number of turns, cross-section area, because the circular becomes pi r squared. Then flux density and resistance come up with the charge they wanted. Then question 3, a ballistic galvanometer is connected to a flat coil having 40 turns of mean area 3 centimeters squared in form of a circuit of total resistance 80 ohm. The coil is held between the poles of an electromagnet with its plane perpendicular to the field and is suddenly withdrawn. You see that word? Suddenly withdrawn from the field, producing a throw of 50 scale division, that is now theta. Find the magnetic flux density at a place where the coil was held, assuming that the sensitivity of the galvanometer under this condition of the experiment is 0.4 divisions per coulomb. Divisions per coulomb. So what does that mean? It means that is a reciprocal 1 over k. You should remember that. So we are interested in the SI unit for you to know that is k or 1 over k. So we know that the number of turns are 40, which is here. Then the area is 3 centimeters squared. You convert to meters squared. Resistance is 80 ohm. Then theta is, there is a division where somewhere here, let me see here, 30. I forgot to write it, but see here 30 divisions. And 1 over k, you should know that. Remember I told you it depends on the SI unit. If it was coulomb per division, we would have written k. But now because it is division per coulomb, we write 1 over k. So 1 over k is 0.4 division per coulomb, per microcoulomb. So convert to coulomb. Then you should remember that therefore k will be the reciprocal, which is now this. So when the coil is suddenly withdrawn, it means that Q is NAB over R. So come and substitute where there is Q, NAB over R. So shall make B the subject, and then you substitute constant theta, resistance, number of turns, and area to give you 0.5 Tesla. Then question 4 came from UNEB 2001, paper 2, question 5D, and says a ballistic galvanometer of sensitivity 2 divisions per microcoulomb is connected across a coil of 10 turns wound tightly round the middle of a solenoid of 10 to power 3 turns per meter and diameter 5 centimeters. When the current in the solenoid is reversed, the ballistic galvanometer deflects through 8 divisions. If the total resistance of the coil and the galvanometer is 20 ohms, find the current in the coil. So when we know the number of turns of the coil is 10, then turns per meter of the solenoid is 10 to the power 3. Deflection is 8 divisions. Total resistance is 20 ohms. So that means that radius is this, because they told you diameter here is 5, so radius is that. And we know that here now you see they have given you, what is it, the division, I'm looking for the sensitivity here. It is division per coulomb. That means it is 1 over K. But we need to get K, so get the reciprocal to give you coulomb per division. So when current is reversed, it means that the direction of the field changes through 180 degrees. Therefore, the charge will be now 2NAB over R. Make B the subject and you substitute. So substitute for the constant, theta, the resistance, number of turns, then pi r squared to give you the flux density. But we know that B is equal to mu naught Ni for the solenoid. Therefore, make I the subject to come up with this. So substitute for flux density, constant, and the number of turns per meter to give you the current they wanted. Then question 5 came from UNEB 2013 paper 2 question 6D and says a such coil has 40 turns of wire and cross-section area 5 centimeters squared. The coil is connected to a ballistic galvanometer and then placed with its plane perpendicular to a uniform magnetic field of flux density B. When the coil is withdrawn from the field, the galvanometer gives a deflection of 240 divisions. When a capacitor of 4 microfarad is charged to 20 volt and then discharged through the circuit, the galvanometer deflection is 180 divisions. Find the value of B if the total resistance of the circuit is 20 ohms. So when the capacitor is discharged through the ballistic galvanometer, capacitance is that, we know PD is that, and the deflection is that. That means that Q is equal to K times theta deflection in the capacitor due to the capacitor. Q is CV. Therefore, K can be got by making K the subject, to give you CV over theta. Then we substitute for C, convert to farad as a unit, then V is that, and the theta is that. So that gives you this as the sensitivity of the ballistic galvanometer. Now, when the coil is withdrawn from the field, we know number of turns that, A is that, deflection is that, resistance is that. So Q is equal to K coil, and we know that Q is, because it is withdrawn, it is NAB over R. Then make B the subject and you substitute. K is already known, theta of the coil is here, resistance is here, number of turns and the area. So that gives you the flux density they wanted. Then question 6 came from UNEB of November 1998, paper 2 question 7B, and it says a capacitor of capacitance 2000 microfarad is fully charged to 10 volt. Okay, when the capacitor is discharged through a ballistic galvanometer, the galvanometer gives a maximum throw of 20 divisions. A coil of 25 turns, each of radius 10 centimeters, is placed with its plane perpendicular to a uniform magnetic field. The coil is connected in series with a ballistic galvanometer. When the coil is rotated through 180 degrees, the galvanometer gives a maximum throw of 15 divisions. Calculate the maximum flux density if the total resistance in the circuit is 3 ohms. So we shall say that when the capacitor is discharged through the ballistic galvanometer, like we have said, we shall say Q is equal to K theta for the capacitor, then substitute for Q, which is this, then make K the subject, and substitute for C, for V, and for theta. Get the sensitivity. Now when the coil is rotated through 180 degrees, it means that Q is 2 NAB over R, where R is the resistance. I know that area can be got from this radius, so it becomes pi r squared. Then you can substitute for K, for theta, for resistance, for number of turns, and pi r squared to get the flux density they wanted. So in the previous video, we talked about the specifications of the Earth's magnetic field, and we talked about the horizontal component and vertical component of the Earth's magnetic flux density, and also the Earth's magnetic intensity, magnetic field intensity. And we saw how to use a deflection magnetometer to come up with these Earth's flux density and also intensity. But what if you are given a ballistic galvanometer? How can you measure the Earth's flux density? So when you are measuring Earth's flux density, the combination of a ballistic galvanometer and the search coil, we shall call it earth inductor. So they can tell you in the question, they can say, describe how you can measure Earth's flux density using an earth inductor, or they can say, describe how you can measure Earth magnetic flux density using ballistic galvanometer and a search coil. They both mean the same. Just as we saw previously that a deflection magnetometer means the same as a tangent galvanometer. So if this is the plane of the magnetic meridian, it means that this will be now BH and this will be BV, therefore the resultant will be in that form. Okay, so if you are to measure, it means that you get your coil and you place it in such a way that the horizontal magnetic flux density is perpendicular to the coil, to the plane of the coil, perpendicular to the coil. And if you are to measure the vertical one, it's also change the direction of the coil to be so that the flux is perpendicular to the plane of the coil. Okay, so you shall say that an earth inductor is an instrument used to measure magnetic flux density of the Earth. It consists of a coil which rotates about an axis. So it must be capable of being set into either horizontal or vertical directions. Horizontal or vertical directions. And it should be in position to turn rapidly through 180 degrees. Okay, so a such coil of known area A and number of turns N is connected in series with a ballistic galvanometer so that the total resistance in the circuit is R. Okay, the such coil is then placed in the Earth's magnetic field with its plane vertical. With its plane vertical, that means there we want to get the horizontal flux density. So the coil is then quickly rotated through 180 degrees about the vertical axis. This reverses the flux through the coil, and the maximum through theta h of the ballistic galvanometer is noted. So the expression for BH can now be got as follows. So we know that from this we are going to substitute for phi 2 and phi 1. Then this gives you this, and BH is that. When where K is the constant of the ballistic galvanometer in coulomb per division. So the search coil is now placed in with this plane horizontal. So there I want to measure BV. So the coil is again quickly rotated through 180 degrees, and the maximum through theta V is noted. So the vertical component will now be given by BV being equal to K theta VR over 2AN. And the value of the Earth's magnetic flux density can be got by Pythagoras theorem. Also, the angle of dip will be given by BV over BH. But we know BV and we know BH. So when I substitute, get this one, when it becomes multiplication, you get the reciprocal of this. So you realize that 2AN cancels. Then K goes away and R goes away. So remain with theta V over theta H. So that means that there are two ways of getting angle of dip, either using flux densities or using the divisions or deflections. Okay, so that we are going through this question. A coil of an earth inductor is rotated 90 degrees from a position in which it is threaded by the horizontal component of the earth's field to a position in which it is not threaded. The throw of the galvanometer is 26 divisions. When rotated through 90 degrees between the positions in which it is threaded and not threaded by the vertical component. So first one was horizontal, now vertical component. The throw is 59 degrees, 59.5 divisions. What is the angle of dip? So in this case, we know that deflection for vertical and for horizontal mean you can get angle of dip using the deflections, which is 66.396 degrees. Then question 2 came from UNEB 2017 paper 2 question 6C, and it says a circular coil of 50 tons and radius 0.5 meters is placed with its plane perpendicular to the Earth's magnetic meridian. It is connected to a ballistic galvanometer of sensitivity this rads per coulomb and circuit resistance of 100 ohm. When the coil is rotated through 180 degrees about a horizontal axis, the galvanometer deflects through 0.8 rads. Calculate Roman 1 the horizontal component of the Earth's magnetic flux density, and Roman 2 the PD across a solenoid of 2000 tons per meter and resistance 5 ohms. That produces the same magnetic flux density as the one calculated in Roman 1 above. So here we shall see that 1 over K is this, meaning that K is the reciprocal. So when the coil is rotated through 180 degrees, it means Q is 2NAB. So you can get BH from here. I think you remember that in the experiment we demonstrated. So A is pi r squared, so you can substitute for K, for theta, for r, for n, and pi r squared to give you the flux density. Then for Roman 2, B is equal to this. So they say that the flux density remains the same. So we shall use this one for B. Then R we know constant and number of times per meter to give you the PD. So that brings us to the end of this video. Thank you for watching, and be reminded